Hello again, Calculus 2 students. We did area, we did volume. Now we are going to arc length. Normally at the beginning of the class, I would have you guys work on a bunch of triangles here. I'm going to do just a few of these. There's a key one that we should focus on. So 3, 4, 5 triangle, you would do that with the Pythagorean theorem. Really all these you would. 3x, 4x, 5x is how that would go. Let's talk about this one. It's hard to see, but that's an f prime of x. So that would be square root of 1 plus f prime of x, each squared, but 1 squared is 1. So we would square f prime of x. I want to focus really, I guess that one would be 13. I want to focus really on this one and show you an algebra trick. So this one in the middle, this is the important one. Okay, so let's do the algebra out. So the radius, or not the c squared, I should say, is 1 dx squared plus f prime of x dx all squared. Okay, so I'm going to multiply this out on this side. So it's 1, it's dx quantity squared, it's f prime of x squared, it's dx squared, and I should square root all that. I'm going to use the same trick we did for the coefficients when we did trig sub. I'm going to pull the dx squareds out. So then I get 1 plus f of x quantities squared, all square rooted. And so this thing I can square root to get dx, and like I normally would, I'll put dx by itself on the end. And so dx would be outside the square root. That is the cute trick they're talking about in here. This is the idea. Okay, you're going to see why that matters here in a second. So this triangle over here is we're going to use the same idea. Fill in English words that fit the blanks below. If f of x means height, well, then f prime of x means slope, and that means rise over run. Okay, a hint about which ones to use. So f prime of x times run would be rise. Putting these ideas together, this triangle here, that's a tiny, tiny, tiny little zoomed in picture of a curve. And so and you can do this on Desmos sometime. If you take any curve on Desmos and you just scroll, you zoom in by scrolling, like to very, 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 very small, they all eventually look straight. So think of that idea here. If you zoom in far enough, these all become little tiny straight lines, and so that's the idea here. And so it says add these labels. Well, the rise on this side would be, actually start with the run. The run would be a little change in x because it's very, very small. What we just said, the rise would be f prime of x times the run. We just said the run was dx. And the c would be the thing I just wrote over there. We just simplified that expression. That's going to be the third side, and that's going to be the length of the arc, right? That's the part. We're saying that if you zoom in far enough, the straight line, this hypotenuse, is the same as the curve if you're in tight enough, and that's the expression we're going to use. So I'm going to go ahead and emphasize this because I feel like the worksheet doesn't make this quite clear enough. This is the arc length formula. We're going to have some different variations for different coordinates. You could also do this with x if you wanted to, but we'll put x1, x2 here, or a to b. Normally I put a to b. That is the arc length formula. That's the point of this page. So anytime you want to do arc length of a curve, take the derivative, square it, add 1, square root, then integrate that. By the way, how would you integrate that? Quite often, it's a trig sub. So yet again, there's a point to trig sub. It comes from applications of calculus. It's not just to torture you. All right. So let's go to the next page. Let's do an integral that, I think we had this maybe the first week of class, and I said, you can't integrate this. And we did it later with trig sub. We're going to take that same curve, so this is a semicircle, but now rather than doing the area or doing the volume, we're going to do the arc length. So here's a semicircle, and I want how long is this? Okay, so it's the upper semicircle, so it's this expression. I meant to graph it there. I didn't listen to my instructions. Okay, I'm going to do a little sample triangle. So if you think about here, if you do a little tangent line, that's the little tangent triangle, if that makes sense. Okay, so the width is dx, so the height is f prime of dx. We'll figure out a formula for f prime of x. Should you simplify? Yes. Remember I said simplify when it's convenient. Okay, so the derivative is, well, the square root becomes 1/2, 1 minus x squared to the minus 1/2. The chain rule gives you a minus 2x. So we can cancel our 2's. It's x over 1 minus square root x. Okay, should I simplify? Yes. So that was the derivative. I should square that and add 1. So x squared, and then the root goes away. If I do common denominator, I get this. And the x squareds cancel, and I get this. Okay, so that's my 1 plus the derivative squared simplifies to that. That was a lot of simplification. Okay, therefore, the hypotenuse is the square root of this, and let's keep on simplifying. Square root of 1 is 1. You should recognize that expression, right? That's the derivative of arc sine x. Okay, so this integral, this arc length goes from -1 to 1, so my x's are going to be -1 to +1. So -1 to 1, and we simplified this down to that, and we know that that's the derivative of arc sine. So integrates to arc sine, plug in -1 and 1. You should get arc sine of 1 is pi over 2. -1, it's minus pi over 2. That adds to pi. Okay, so pi is our answer for the arc length of that curve. And by arc length, I mean how long it is, right? If you pulled it out taut like a piece of string, how long would it be? And we already know that because for arc length for a circle, we already have a name for that. We call it circumference, and 2 pi r is the formula. R is 1, so it'd be 2 pi, but we have a semicircle, right? We have half of it, so pi makes sense. Okay, but now here's a completely different curve. So it lies above the x-axis. This is a frowny parabola, and it crosses the axis when x is, I think, 4 and -4. You can graph it on Desmos and see. So 1, 2, 3, 4, 1, 2, 3, 4. So, and then in the middle it goes up to 8. So it looks like this. And they're asking for just this part. How long is that if you pulled it taut? Okay, and I graphed it in the wrong spot again. Please forgive me. Here's a sample triangle with it on this side now, kind of hanging out in midair. Okay, take the derivative. Should you simplify? Probably, but the derivative is just, let's see, minus 2x over 2. So you get negative x. And the hypotenuse, well, if I square that, it is positive x squared. So 1 plus x squared. And then I'm going to go to the next page here. Let's pull this up a bit. So there's the beginning. And now it says write an integral for the arc length. Well, we just figured out that that is the expression in the middle. 1 plus the derivative squared. And we're going to go from -4 to 4. By the way, how do you do this? You do it with trig sub yet again, but I don't want to. You can use Wolfram Alpha or whatever you want for this problem, and you get this disgusting answer. Is that what I get? Sure. Okay. Now, they're giving up later than I did, but the next one they say, hey, just use Wolfram Alpha. So all I really need to do for arc length, it's not too much work. It's just 1 plus the derivative squared, square root. It's just plug and chug the formula. They give you the links, 1 and 2. So square root 1 plus, now ln's derivative is 1 over x, square that. Okay, you can simplify and make this a trig sub problem yet again, but instead we'll use Wolfram Alpha. Let's go ahead and check what the answer would be. It's worth mentioning that I just lied. I did not use Wolfram Alpha. I used Desmos, and it gave me a decimal here. Wolfram Alpha would give you a better exact answer, but there's a nice approximation, and that's good enough for me. All right, so that's arc length. Next time I will probably use Desmos rather than the .cam because we're going to be doing parametric and polar coordinates, and I want to show you how to use the computer for those. I am not going to do the Plickers problem here. You notice I didn't do it last time. You guys can pretty much forget about the Plickers problems at this point. That's all right. Okay, see you next time. We'll talk about parametric coordinates, and then later we'll talk about polar.